Good evening, everyone. Firstly, I'd like to thank the organizers, especially Samriddhi, for accommodating my talk in this tightly packed schedule. Today, I'll be talking about page curve-like dynamics in interacting quantum systems. This was done in collaboration with Abhishek and Manas, who are from ICTS, and it's based on this recently archived work. So the basics of this, the background of this work is basically an open system where you have a system which is coupled to some bath, and at t equals to 0, the system is filled and the bath is completely empty. So they are completely decoupled. But as time goes on, the particles from the system leak into the bath, and the particles from the system leaking into the bath increases the entanglement between the system and the bath. And eventually, at large time, as all the particles have left the system, it is again decoupled from the bath and the entanglement goes to 0. Now, this behavior of the entanglement, where it first increases, reaches some maximum value, and again goes back down, is what is known as the page curve. In some other context where this kind of a setup was motivated from is like if you consider system to be some black hole and the bath to be some surrounding radiation field, then what Hawking had shown that this black hole radiates thermal radiations, which are known as Hawking radiations, and he showed that initially when say the bath is in some vacuum state and the system and the bath are in a pure state, they evolve into some thermal state at late time. Now this violates unitarity in quantum mechanics and leading to the famous black hole information paradox. So this is one schematic of this paradox which was taken from this particular paper, where you expect the entanglement to behave like this, but from Hawking's semi-classical calculations, we see that it grows like this. Now, although this background is quite interesting, but our motivation for this work is purely based on the behavior of entanglement in interacting systems, and which is in itself an interesting problem. And a while ago, like last year, this paper came out where the authors have investigated this kind of a behavior in entanglement for a non-interacting fermionic system, where they couple a fermionic system to some fermionic bath, and they get this page curve-like behavior. And a very obvious question in such a setup is to ask, what happens if I turn on interactions? For one, the thing becomes extremely more complicated and much less analytically tractable. So what we consider is a fermions in a 1D lattice with integrable as well as non-integrable interactions. And
So the bath is something which exists, but it's not that from the system all particles leave to the bath. I mean, I don't know what kind of bath you are talking about.
yes, so basically, like if you can think of it like in the long time limit, like if the number of particles in the system, the particles will completely evenly distribute between the system and the bath.
Yes.
And the bath is infinitely much larger than the system. So the effective number of particles in the system, you can think of it as like 0. So effectively, it's like our system is in a vacuum state and the bath is in some state and they are decoupled, and thus the entanglement goes to 0. So using this Jordan-Wigner transformation, you can map this fermionic problem into the well-known XXZ model with some next nearest neighbor interaction, where this is the hopping term, this is the integrable interaction, and this is a non-integrable interaction. Due to time constraints, I'll only talk about integrable interactions. So in our model, we have a lattice-like structure like this, where the red dots indicate the system, and this is the system Hamiltonian, where we initialize system in two different kinds of initial state. First is this polarized initial state, where the system is completely filled, and secondly, it's in some infinite temperature half-filled state. And then the bath is always in an empty state, which is like a vacuum for us. And the system bath Hamiltonian is just given by some XXZ coupling. So coming to our results, first of all, we plot the entanglement, the fluctuations of the particle numbers in the bath and the mean particle density in the bath as a function of time. And we can analytically, using perturbation theory, we can analytically compute the early time behavior in this case, where we see that the entanglement grows as some t square log t in the leading order, and the fluctuations and the mean density of the bath grow as t square by 4. So one important thing here is that in these papers here, they have reported that the entanglement for this interacting system, they grow as t to the power 1 by 4 for a domain world state. But our study is not a contradiction to this, but this faster growth, which is t to the power around 0.3, can be explained from the fact that the system is finite and the particles encounter the finite side wall of the system and get reflected and further increase the entanglement between the system and the bath. And another important point of difference from a non-interacting case is that we don't need any defect to get a power law behavior in the entanglement for this case, whereas in non-interacting case, you get a logarithmic growth in entanglement. And unlike the non-interacting case, we also see that the fluctuations in the bar do not agree with the entanglement entropy. And as I had mentioned, we also consider the infinite temperature state. Now, we use something called tensor networks and matrix product states to simulate these things because these are very large systems. And a caveat about this MPS is that, which is matrix product states, is that it's very hard to write down the MPS for some arbitrary state. So we use this scheme to construct this infinite temperature state where we start with some polarized down state, which is a product state, and it's very easy to write down the MPS for. And we apply hard random unitaries on this. And the depth of the circuit is of order of the system size. And as a result, the system reaches some high entropy state, whereas the bath stays in the polarized down state. Now, for this case, when we plot the results, we notice that the entanglement goes faster compared to the case when the system was completely filled. Now, this can be explained from the fact that, like, since this growth of entanglement explained from particles leaving the system into the bath, it was shown that when you have a domain wall state, like the density profile broadens faster when you start from an infinite temperature state compared to when you start from a fully polarized state. Now, coming to this something called the Boltzmann entropy. Now, for the non-interacting case, as in this paper here, the authors showed that the entanglement entropy, which is a fine-grained quantity, with the hydrodynamic entropy, which is again a coarse-grained quantity, and they got a remarkable agreement between the two. So we wanted to see if we can find something like this, and where we can compare this fine-grained entanglement with some coarse-grained Boltzmann entropy if we turn on interactions. And this coarse graining is done over spatial bins. And the coarse graining goes as follows. Like, we have this lattice, and we take some bin of some fixed size. And for our case, we set the bin size to be the same as the system size. And we compute the average energy and average magnetization of this bin. This gives the macro state the bin is in. And using this macro state, we compute this using time dynamics, using some tensor network techniques. And using this macro state, we compute the corresponding grand canonical ensemble. That is basically computing the beta and the mu for this average energy and average magnetization for this particular bin. And once we have this, we can compute the Boltzmann entropy of this bin with this formula. Note that this is a purely mathematical construct. We are not saying that this bin is in some thermal equilibrium, which it is definitely not in. And once we have this, we can compute the entropy of the system as just by setting the bin to be the system bin. And if you want to compute that of the bath, you compute all the bins in the bath, you compute the entropy and then add them up and you get the entropy of the bath. And by doing so, we compare the two, entanglement and the Boltzmann entropy here, and we plot both the system bath and the entanglement of the system bath. And we see that when we, on the left hand side, you have the polarized case where we start from the filled initial state. We do see an page curve like behavior for the entanglement of the system, which is this red curve here. But for the bath, we see that the entanglement keeps on increasing till it saturates to some value because our bath is finite and we have finite number of particles in the system. On the other hand, when we start from an infinite temperature state, we see that this agreement is much better. But in this case, like if you see that since the system is an infinite temperature state, and as expected, we start from the infinite temperature entropy, which is Ls log 2. And slowly, after some time, as the system starts, and from this point, the system can only lose its entropy and it comes down. And eventually, it starts agreeing with the entanglement entropy after the page time. Whereas for the bath, you start with this completely empty state, and as the particles come in, its entropy increases, and it agrees with the entanglement entropy till before the page time, and it again saturates to some value given the finiteness of the setup. So I'll leave the summary slide here, and so basically we obtain a page curve like behavior for entanglement interacting fermions coupled to a bath. And we see that interactions lead to qualitative and quantitative differences when we do not have interactions. For example, we do not need a defect of power law behavior, bath fluctuations do not agree with the entanglement, and this interaction enhances the growth to sublinear compared to logarithmic when you don't have interactions. And we also construct a coarse-grained Boltzmann entropy, which has a similar behavior to the entanglement. We also have results for non-integrable systems and also when the bath is non-interacting, which I can discuss with you after the talk. And thank you for your attention, and I'll take questions.
So why do you need such large systems? Not like
So, like, if you see that already here, like, you have your system. The system, the particles keep losing. The system keeps losing particles, and the particles eventually, like, if you look at a better example, if you look at a density profile here, you see that the density of particle, it keeps propagating to the right.
yes.
And if you don't take the bath to be quite large, this will eventually get reflected on the finite edge of the bath and come back, and it will affect the entanglement of the system and the bath, which is not what we want. We don't want to see this finite size effect in our dynamics. So we want the system to be, bath to be as large as possible.
And one more question. So, like, what do you think? Why you don't need defect in case of this interacting system? Like, you are not needing any defect for the page curve, like.
We don't know why we do not need a defect here. Like, it's what interaction does. It just turns out that if you put interactions, you get, this is how the entanglement behaves. Whereas if you don't have interactions, like Cardi and Calabresi had computed that, and they explicitly analytically showed that it grows as logarithmically. Whereas in our case, we see this power law behavior.
Okay, nice to thank you.
And one more important point is that you see this logarithmic behavior, t square log t behavior in the initial point. And this is actually the point where the interaction timescales where the interactions do not kick in. So this is an exact result, and this is independent of the interactions.
Okay, so thanks to the speaker.
Sorry, Abhishek wanted to ask.
If I consider like the comparison between Boltzmann entropy and entanglement entropy is a bit perplexing. If I compute the Boltzmann entropy for the full system, it has to increase.
Yeah.
But for the entanglement entropy, of course, if I compute the entanglement entropy for a pure state, then it's just zero.
Yeah.
So if there's a complementarity with the entanglement entropy, that is like, it's only when you would make a bipartition that you get depleting in one side and increasing on the other side. That doesn't exist with Boltzmann entropy. So the fact that they like, you know, the Boltzmann entropy dynamics and entanglement entropy dynamics agrees, could you comment on why that is so?
I mean, if you just look at the way we have constructed the Boltzmann entropy, like, it's pretty obvious. Like, if you start from the polarized initial state, the system's Boltzmann entropy is zero because it's just one particular, like, so this Boltzmann entropy, the way we are computing is basically counting the number of microstates corresponding to this macrostate in this bin here, right? So if you start from some polarized initial state, we just have just one microstate, and that leads to the zero Boltzmann entropy. Now, if the system starts losing particles, it will eventually move into some superposed state, and which itself will have a higher entanglement, higher entropy. So this increase in entropy is understandable. And again, like, in the late time, you see this fall in entropy because the system is losing particles, eventually moving towards, again, a polarized down state, which again has a zero entropy. The same for the bath. The bath just keeps increasing because you have a constant influx of particles from the system till some point when they could use a finite number of particles. Is this a comment that you were looking for? You wanted some? Okay, sure, yeah.
Okay, so thanks to speaker.